Hi, thank you so much for joining me. In this video, we're going to cover a topic that is somewhat unique to AP chemistry, but I think is so helpful for Gen Chem and IB Chem. I think it really adds clarity to some of the units and conversions that we do in thermodynamics. And that concept is the mole of reaction. I'll be honest, when I first heard it, I thought it was a little odd. But now that I have used it, I really like it, and I think it helps students a lot. So let's dive in. If we have a reaction, for example, this shows the combustion of butane. It's balanced with a whole number ratio, and I am given a value for the enthalpy of combustion of minus 5271 kilojoules per mole. And typically that's the unit that's given in books. But per mole of what? That is not clear at all. That's the clarity that we want to achieve in this video. It is implied, it's per mole of each substance as the reaction is balanced, which again is a mouthful. For example, it's not uncommon to balance diatomics by using fractions. So we could have balanced this with fractions and had 4 CO2 and 5 waters, and hopefully it is intuitive to you that the delta H would be half. So that would be per mole of these coefficients as balanced. And this is all, like I said, implied. And the mole of reaction can add some clarity. So what is a mole of reaction? That sounds kind of odd when you think about it. How do we have a mole of reaction? Well, let's think about it, and I thank Paul Price for this. Let's represent that as if the reaction happens a mole of times. So 6.02 times 10 to the 23rd times. So every mole of reaction, or every time this reaction occurs, 6.02 times 10 to the 23rd times, I'm going to consume 2 moles of butane, 9 moles of oxygen. I'll consume 8 moles of carbon dioxide and 10 moles of water. And so you can think of it as a measurement of the number of cycles that the reaction goes through. So now what we would have is a new conversion factor that would be for every 1 mole of reaction, 2 moles of C4O10 are consumed. For every 1 mole of reaction, 9. And you could flip-flop these conversion factors at your convenience, depending on the direction you're going. And likewise for the CO2 and for the H2O. All right, and this would have applications to other units in chemistry as well. I'm just going to focus on it in terms of our thermodynamic properties. So let's take a look at an example of this with the combustion of butane. I want to go a forward one, and then I want to do a reverse one so you see how it applies. So how much energy is released when I have 300 grams of butane and excess oxygen? It's very important that if you have a reaction, your energy is going to be limited by your limiting reagent, just like the grams or volume or amount of product is limited by the limiting reactant. In this case, I have excess oxygen, so I can focus on my butane. So I have 300.00 grams of my butane, C4H10. I need to get to moles, so I can relate moles of butane to moles of reaction. So 1 mole of butane is 58.12 grams. Whoops, that's a 2. Okay, now this is where our new conversion factor comes into play. In this reaction, for every 1 mole of reaction, or 6.02 times 10 to the 23rd cycles, I'm going to consume 2 moles of butane. Now we can use that given enthalpy of the combustion reaction as minus 5271 kilojoules will be released for every 1 mole of reaction. So now if you want to cancel grams, moles cancel moles, mole of reaction cancels mole of reaction, and I'm left with kilojoules. This is the key. Prior to that, we didn't really have proper cancellation of units. And so I really like doing this way. In a sense, it adds another step, but I think it's a valuable step to add. And if I did my algebra right, and you always need to check me on that, 1.360 times 10 to the 4th kilojoules would be released for 300 grams of methane. All right, let's take a look at this next one. This next one, I intentionally put in a limiting reactant problem. And it's a little bit like a question we saw on an AP test a year or so ago. So I'm going to do a start of a BSA table. I have 0.350 moles, and I've got 0.450 moles, and I've got 0.30 moles. And I need to calculate the enthalpy of the reaction. So we want to get it in per mole of reaction. So the first step is to find my limiting. A quick way to do that is to divide what you have by what you need. Okay, and if I do that, I get obviously 0.35, 0.1125, and 0.15. So what that shows us is that it is our NOCl that is going to be our limiting reaction. So it's going to dictate, it is what limited that amount of energy that was released. And I want you to look, just hold this little number in your mind for just a minute. I think you're going to see it crop up again in kind of an interesting way. So I'm going to start with my limiting. I've got 0.450 moles of NaOCl. Okay, and times 1 mole of reaction for every 4 moles of NaOCl. So that means that I'm going to have 0.1125 moles of reaction occur. Okay? Isn't that interesting that the way I evaluate my limiting ends up giving us that mole of reaction? That should have been a 4 right there. I'm glad I caught that. So now my delta H naught for my reaction is going to be 135 kilojoules. That's what was released for every 0.1125 mole of reaction. And double check my math. I feel pretty good about this one, but we always want to double check my math. I got 1.20 times 10 to the 3rd kilojoules per mole of reaction. Okay, so let me rewrite that. Minus 1.20 times 10 to the 3rd kilojoules per mole of reaction. And you may be asking at this point how I knew it was negative, and it's because the process tells me that energy is released, therefore it is exothermic reaction. Okay, thank you so much. I think this is a very important concept that we want to keep in as part of our mathematics and our conceptual understanding for the rest of this unit. Thanks so much for your time.